All right, welcome back, and we're on conditional probability, lesson 8E, last lesson of our unit. And conditional probability asks us to find a probability when you already know something has happened. And the best way for us to think about this is the idea that you are cutting down the sample space. So I'm just going to kind of put that in quotes. So we're sort of cutting down the sample space so we can isolate more on what's going on for this particular situation. So to kind of warm this up, and if you've already done a sweet task, then this is going to make a lot of sense. If you haven't done a sweet task yet, we will get to that here in class, and I think it'll help kind of reinforce some of these concepts. So the warm-up problem here is that we've got the manager for a brokerage firm that has noticed some of the firm's stockbrokers have selected stocks on research, and that would be event B, and others tend to follow their own instincts. And then we had others that, some of the stocks went up in value, some of the stocks went down in value. So if I wanted to find, out of all these brokers, because there's 100 total, and you can kind of see that here in the lower left-hand corner, if I wanted to find the probability of event A that a broker picked stocks that went up, this is the total number right here. That 60 is the total number of brokers out of the 100 who picked stocks that went up. So that reduces down to 3/5. Now, if I wanted to do the complement of A down here, that's pretty easy to do. Well, the complement is just going to simply be 1 minus the probability of A, if you remember that from the last video, so 2/5. If you went ahead and did the 40 over 100, you'd come up with the same result as we just did here. Okay, so what's the probability that a broker used research? Well, out of the ones that used research, the total number was 45. And you can get that from the edge of the table here, the margin of the table, if you will. This is called a marginal probability. And you get that from using the margins of this two-way table here. So 45 out of 100. Now if you reduce that down, that's 9 out of 20. So what's the probability that they did not use research? Well, if 9 out of 20 is the probability they did, then 1 minus 9 out of 20, or 11 out of 20, that's the probability they did not use research. Okay, now here's an interesting question here. There's what's the probability that you picked a broker who uses research and pick stocks that go up? Well, the ones that used research and the stocks that went up, well, that's right here in the table, because that's where event A and event B intersect. If you drew event A as a road going north-south and event B as a road going east-west, they'd intersect right here in the table. So 30 out of the 100 are brokers who used research and their stocks went up in value, so that's 3 out of 10, or 30%. Okay, so I could go through a big long formula here, and it looks kind of complicated because it is. The conditional probability of event B, or event E given event F, is written as the probability of E and this vertical bar F. So we know F has occurred. Okay, so we already know that F has occurred. We've kind of imposed some sort of condition on this situation where F has already occurred. And in this case of the previous problem, well, we knew that the broker picked, well, we'll get back to another example in a minute. I think it's going to make more sense in a moment here. I shouldn't use that one. If I wanted to find the probability that something occurred knowing something else has happened, I've got to take this into account. So let's go back and do this situation. What's the probability that I have a broker that did not pick stocks that went up, assuming they did not use research. Okay, so let's start with the fact that this B complement, we know. Okay, so we know for sure that what happened was event B complement happened. So what is event B complement? That means that the broker did not use research at all. So we're going to focus in on just the ones that did not use research. Okay, so if I know that that occurred, then I know I'm cutting down my sample space here to just 55 brokers. Okay, I'm not going to worry about anybody else. I'm just going to worry about the ones that didn't use research, and that totals 55 of them. And I'm interested in the probability that the stocks did not go up given the fact they didn't use research. So because they didn't use research, again, I'm going to ignore everything else and just focus on this line of the table right here, because I know that definitely happened that they didn't use research. There are 25 out of the 55 that pick stocks that didn't go up and they didn't use research. I know I should have probably said that a little bit differently, so let's try again. There's 25 out of the 55. Out of the 55 that didn't use research, 25 of them picked stocks that didn't go up. So that's how I can come up with the possibility of 25 out of 55, the probability rather. So we know no research used. Okay, so the probability of getting no research used, or there was 55 of those people that didn't use research and 25 of them had stocks that did not go up in value. So you reduce that down to 5 out of 11, and that's the answer for part A. So this is what's called a joint probability or a conditional probability, depending upon the situation that you have. All right, so let's go on here. If you toss two fair coins, at least one of them came up heads. So what's the probability they both came up heads? All right, well, if you toss two fair coins and at least one came up heads, that is what you know for sure. Okay, so you know this happened. Okay, we know that that happened. So now what I need to do is I need to come up with a sample space based on knowing that information. And that should be pretty easy to do here. If you toss two coins, at least one of them came up heads. Well, maybe the first one came up heads, second one came up tails. Maybe the first one came up tails, the second one came up heads. That satisfies it. And maybe we have two heads. That's entirely possible as well. Okay, now we can't have two tails because we know at least one of them came up heads. So out of those three outcomes, there's only one of them that says both came up heads, and that's this one right here. So the probability is 1/3. So already you're seeing that you might have to talk yourself through these probability problems with conditions as opposed to trying to just kind of work it out yourself just with this formula, because sometimes this formula can be really clunky to use. I'd rather just kind of think carefully about the situation, and I find I'm doing it much more effectively than following a formula with symbols that are hard to read. All right, so this is an interesting situation here. Let's see if we can talk about the probability that a WHS student, and I know this is a hot button topic with a lot of students, is the parking. Okay, so let's say that he's got the probability that you park in a no parking zone and get a ticket is 8%. The probability that he parks in a no parking zone is 15%. So on Friday, Tim finds someone in his park, has to park illegally. What's the probability that he will get a parking ticket? All right, well, those times that he has to park illegally, this is the known information here. Okay, that's the known information here. So if that's the known information, that's what goes in my denominator to figure out the conditional probability. Okay, so the probability that he gets in a no parking zone and gets a ticket is 8%, and that's what goes in my numerator. So really it's just going to be 8 out of 15 if you do away with the decimal points there. So the probability that he gets a ticket, knowing the fact that he's illegally parked, is going to be slightly more than half. I don't know how lucky the guy is as a result, but there you go. So again, the idea is let's cut down the sample space. Let's see if we can kind of focus in on what we know happened and then adjust it from there. Okay, now again, there's a product rule and then there's a product rule for independence, and the idea is you can multiply probabilities together regardless if they're independent or conditional, and you'll see what we mean here by this. If you roll a coin or flip a coin and roll a die, then the probabilities are independent because they're two independent events. You can still multiply them together. So what you're trying to do is say, first of all, that this is independent. One outcome doesn't depend on another. You want to find the probability that the coin lands heads up. Well, that's 1/2. And the die shows an even number. That's also 1/2. So the probability that both of these things occur simultaneously is 1/4. Okay? So come over here and let's talk about this in number 6. You roll a fair 6-sided die twice. The first roll shows a 5 and the second roll shows a 6. Well, honestly, does the probability matter here? Are these independent? And the answer is yes, they are independent, because it doesn't matter what you got on the first roll. The second roll is definitely going to act independently. It doesn't really matter what you got on the first roll. You could have gotten a 2 on the first roll and still gotten a 6. So the probability of getting a 5 is 1/6. The probability of getting a 6 is 1/6. So the probability of getting that specific outcome of a 5 and a 6 in order is 1 out of 36. Okay, hopefully pretty easy so far. All right, now there are 8 shirts in your closet, 4 blue and 4 green. You randomly select one to wear on Monday and a different one on Tuesday. What's the probability you get blue shirts both days? Okay, well, in order for this to happen, then you have to get blue on Monday and blue on Tuesday. All right, so if you've got 8 shirts and there are 4 blue and 4 green, Monday comes first. In order for you to get this right, well, you've got 1/2 of your shirts are blue. So the probability you select a blue one is 1/2. Now, things change on Tuesday, because if you're not going to rewear the shirt, if you're going to throw it in the laundry basket instead of putting it back up or putting it back up in your closet, assume that's going to be the case because you wear a different one on Tuesday. What's the probability you get another blue shirt? Well, there's only 7 of them left if you stop and think about it for a minute, because you've already accounted for the blue shirt. So there's 7 of them left, and 3 of them are blue because you started out with 4 and now you've eliminated 1 by wearing it on Monday. So these are dependent events. What happened on Tuesday is sort of, what your probability is depends on what happened on Monday. So that's why they're dependent. You multiply those two together, 3 out of 14 is the correct probability that you wear blue shirts on both days. Okay. All right. Basket contains 5 apples and 7 peaches. You randomly select one piece of fruit and eat it. Then you randomly select another piece of fruit. You want to find the probability that one is an apple and the second one is a peach. Well, finding the probability that the first piece of fruit is an apple shouldn't be too bad. There's 12 pieces of fruit altogether in this basket, and that's 5 out of 12. Now, here's the catch. If you eat an apple, that's going to change the probability of you getting a peach, because now for the second piece of fruit, you've eaten one of them, so now you're down to 11. And then this is going to give me an opportunity to say, okay, well, there's 7 peaches out of the 11, and this works out to be 35 out of 132 when you multiply those together. So that's the situation there with that one. Again, you just have to kind of talk yourself through this and figure out what's going on. This is, what you know. The known information is that, you've already eaten an apple, so now you have to find the probability you've eaten a peach, given the fact you've already eaten an apple. Okay. This one's a little bit interesting here. In a class with 2/5 of women and 3/5 of men, 25% of the women are business majors. Find the probability that a student chosen at random is a female business major. Okay, well, the chances of selecting a woman are 0.4, or 2/5, and then the chances of selecting a woman who is also a business major, well, you have to select the lady first, and the chances of that is 0.4. Then you've got to, within that set of ladies, you have to choose a business major. And the chances of that are 25% of the women are business majors. So now that you've selected one of the ladies, you have to select one that is a business major. And that probability is 0.25. So you've chosen a lady, so now you've got to find the probability of one of those ladies being a business major. So 0.10 is going to be the probability that you select a female business major from the entire class. Okay, here's a really good one. This is an excellent test question right here. Calculator requires both a keypad assembly and a logic circuit assembly. 99% of the keypads are satisfactory, 97% of their logic circuits are satisfactory. What's the probability that you'll get a calculator to run correctly? Well, these two are independent of each other. If they're assembled on different lines here, then the probability you get a keypad that works is 0.99. And the probability that you get a logic circuit that works is 0.97. So you're going to multiply those two numbers together in order to get the probability that you get a calculator that works completely. So let's get that total brought up here. I'm going to do this on a calculator off screen. And that probability is 9603. So about 0.96 probability that you get an assembled calculator that works perfectly. Okay, well, what's the probability of getting a calculator that doesn't work perfectly? Well, then that's a complementary event. So I'm just going to make this really easy here. And we're just going to do the complementary part, and it's 0.0397 that you get a calculator that does not work properly. Okay, so that is a quick little tutorial on conditional probability, and I hope that this has been a good thing for you. And go tackle the practice problems, and good luck.